Hi, so today we will be talking about uncompetitive inhibition. This is an example of reversible enzyme inhibition. And what happens is, suppose we have an enzyme. In a normal case, it will bind to the substrate, form the enzyme substrate complex, which will go on to form the product. In uncompetitive inhibition, there is an inhibitor which binds to the enzyme substrate complex and forms the enzyme substrate inhibitor complex, which is inactive and cannot produce the product. Now, uncompetitive inhibition, to be honest, is very rare, but we have one enzyme known as acetyl cholinesterase, which is present in the postsynaptic junction, and we have nicotinamide, which is an uncompetitive inhibitor for acetylcholinesterase. Apart from nicotinamide, there can also be certain tertiary amines which can behave as an uncompetitive inhibitor for the acetylcholinesterase enzyme. Now we will try to mathematically derive the rate equation for the uncompetitive inhibition reaction. So normally I will write down the equation or the pathway of an enzymatic reaction, and in the meantime I would recommend you to go and check my video on Michaelis-Menten equation and also competitive inhibition, so you will get an idea about the derivation of this sort of equation. And apart from that, I have also described a concept known as the steady state approximation, which we will use in this case as well, and you will get an idea from. So now, if you have seen my previous videos, you know that what we need is we need to know the concentration of enzyme substrate complex at a particular time. Now we also have one unknown, that is the amount of free enzyme, which is this one over here, and we don't know how much of it is left in a reaction mixture. So we'll try to figure that out in terms of what we know or what we can use in our derivation. So we can write down the amount of free enzyme is the total amount of enzyme initially present in the reaction mixture minus the amount of enzyme which has bound to the substrate and formed the enzyme substrate complex minus the amount of enzyme which has bound to the substrate and then further being bound to the inhibitor, forming the enzyme substrate inhibitor complex. Now if you have checked my video on competitive inhibition, you can know that we can write this part of the equation, or the enzyme substrate inhibitor complex part of the equation, as ES I by KI. Okay, so we can write this down as equal to E naught minus ES 1 plus I by KI. So I will take the liberty of writing this part of the equation down as alpha. So we can write this as E naught minus alpha into ES. Now while deriving the rate equation for enzymatic reaction, we will use the steady state approximation, which tells us that the rate of change of the enzyme substrate complex over time in steady state is 0. So what we will do is we will exploit this as des by dt can be written as K1 into ES minus K minus 1 ES minus K2 ES. So this is the term that forms the product. This is the term that forms the enzyme and substrate reversibly from the enzyme substrate complex. Now what we will do is we will use the equation that we derived here for free enzyme. So this was for free enzyme present at the time of the reaction, and we'll put it down here. So we can write this as E naught minus alpha into ES into S minus K minus 1 ES minus K2 ES. Now we will expand this term. K1 E naught S minus alpha K1 ES S minus K minus 1 ES minus K2 ES. So what we can do right now is we will take ES common from these three terms of the equation. So we can write this down as K1 E naught S minus ES alpha K1 S plus K minus 1 plus K2. Now from the steady state approximation, we know that the rate of change of the enzyme substrate complex over time, or DES by dt, is equal to 0. So this part of the equation becomes 0, or we can write it down as ES into alpha K1 S plus K minus 1 plus K2 equal to K1 E naught S. Okay, now we can write this as ES is equal to K1 into E naught S divided by alpha K1 S plus K minus 1 plus K2. Okay, now we will divide the numerator and the denominator by K1 is equal to E naught S divided by alpha S plus K minus 1 plus K2 by K1. Now if you have seen my previous videos, you know that we can write this part of the equation as Km, or the Michaelis constant for this particular reaction. So we can write this down as E naught S divided by alpha S plus Km. Now we know that the rate of an equation, or the rate of this enzymatic reaction, is V is the rate of formation of the product, which we can write it down as K2 into ES. Now this term over here is basically ES, which we derived, so we can write this as K2 into E naught S divided by alpha S plus Km. Now we can write K2 into E naught as Vmax, and I will elaborate the term alpha over here. So this equation becomes V equal to Vmax into S divided by alpha was 1 plus I by Ki plus Km. So this over here is the rate equation of an uncompetitive inhibited enzymatic reaction. Now we will derive the Lineweaver-Burke plot for this equation, which is just taking the reciprocal of the left hand side and the right hand side of that equation. So it becomes 1 by V is equal to V max into 1 plus, sorry, I made a small mistake over here. It would be equal to 1 by V max into 1 plus I by Ki plus Km by V max into 1 by S. So this is the Lineweaver-Burke plot for this equation, and what we will do now is we will draw a nice plot and see how the Km and Vmax behaves in an uncompetitive inhibition. So the x-axis is 1 by substrate as usual, and the y-axis is 1 by V. So when 1 by S is equal to 0, then 1 by V becomes 1 by Vmax plus 1 plus I by Ki. So if normally, so in a normal case, suppose this is the Lineweaver-Burke plot for a normal enzymatic reaction without any inhibition, where this is 1 by Vmax and this is minus 1 by Km. So what happens over here is Vmax or 1 by Vmax increases. So the plot will shift up. So this, or the y-intercept becomes, I would write it down here only, it becomes 1 by Vmax multiplied by 1 plus I by Ki. Okay, now what happens when 1 by V is equal to 0, or we need to find out the x-intercept of this equation. So we can actually write it down here. It becomes 1 by S Km by Vmax is equal to minus 1 plus I by Ki by Vmax. So this cancels out, and or 1 by S becomes 1 by Km minus 1 plus I by Ki. So this will also move further away from the 0. So it will become this, and this is 1 minus 1 by Km into 1 plus I by Ki. So the equation will become something like this. Okay, so 1 by Vmax increases and Km decreases. So as you can see, the slope of the equation, or Km by Vmax, remains constant even in uncompetitive inhibition. We saw that the slope changes in competitive inhibition, but it remains same here. What happens is 1 by Vmax increases and Km decreases. Okay, so if you like the video, please like, share and subscribe, and let me know down below in the comments if you have further questions, suggestions, etc. Thank you so much.